Well, hello. Some things in life just don't seem right. And the video actually the clip out of the video I'm going to play is one of those things that just isn't right. Basically, they're saying that there's no way you can tell that the earth is rotating. And I disagree with that severely. So, first, let's play the clip.
If you're not accelerating, you're just moving at a constant speed in a plane, or now. I mean, that's essentially what we're doing now. We're moving around the sun at effectively constant speed. Then you can't tell. So there's no experiment you can do. We could look at the decay of a radioactive nucleus or some electricity and magnetism or bounce a ball, have a pendulum, whatever it is. And there's no experiment you can do to tell you whether you're moving or not. Therefore, that concept has no meaning because you can't measure it. And that's led Einstein to relativity.
Wow.
So that's the basis of general relativity, which is our best theory of the universe.
One other thing you might want to consider is Foucault pendulum. That's a big pendulum in a lot of museums that's swinging, and all during the day it rotates. Well, it doesn't rotate, it changes where it's swinging. That's positive indication the earth is rotating. The sun comes up and the sun goes down. That's positive indication that the earth is rotating. There's retrograde motion in the planets. That is positive indication that the earth is rotating around the sun. So there are many, many, many indications that we are in motion, perfectly provable, and that it is us that are moving, not the other things. This is our setup at the location where we will have a rotating structure that will generate 1 g of force along the blue line once it's spun up. It is also our setup as we sit in our spaceship waiting to start accelerating at 1 g of force, pushing everything towards the laser. First, let's look at our setup here, the components. We have the laser on the left there, and then we have the half silver mirror that's set at 45 degrees to the laser beam. The half of the light that manages to go through the half silvered mirror goes on over to a fully silvered mirror on the right, which reflects its beam back towards the detector. And the part of the beam that is reflected travels down to the fully silvered mirror on the bottom there, and it reflects its beam back into the detector also. And located halfway between the two fully silvered mirrors is our detector. For ease of explaining and understanding, we have decided to assign the distance between the half-silvered mirror and the fully silvered mirror is 1 unit. Now, what you use for your units is strictly up to what you want to use. All we know for sure is that it is 1 unit. And everything measured is just a percentage of 1 unit. Now, in this setup, we're going to have one rotating experiment as shown on the top there. And the rotational vector will be down towards the bottom picture. In the linear accelerating experiment, we're going to have a thrust vector that's going to be pushing us towards the right. These are the angles each beam forms when it is reflected or split by the mirror. The two legs being 1 unit long, and we want everything equal on the two paths for future comparisons. we wind up with a configuration where all angles are 45 degrees. This shows the incident and reflected angles for the beams as they get reflected off the two mirrors. Now at this point we need to understand that according to present physics, all physical laws are the same in every inertial reference. In this case, we want to make specific note. The angle of incidence for any mirror produces the same angle of reflection. Okay, back to our starting alignments. Right now, some remote entity starts accelerating our ship away from where we are, and it also starts the rotating experiment rotating. So we are now on a journey at 1g acceleration. There is a transmitter located at the point in space where our ship will be when 306.64 days have passed, as shown by a timer on Earth. This transmitter will signal us to check our experiment. There is a timer close to the rotating equipment that will alert the rotating control crew at 306.64 days, which is exactly when we will receive the signal from the previously remotely placed transmitter. Both of these signaling devices have a zero velocity relative to the Earth. And yes, we are an intelligent species. We can measure the forces and speed the remote transmitters undergo as they are sent to the remote locations, and thus adjust their timers to the Earth timer. When the rotating control crew opens their experimental cover, they see this. As expected, nothing has changed due to the rotation. When we open our cover, we see this is not what we really expected. But, assuming the theory of relativity and the Lorentz transforms are proper, such that the twin that travels away from the Earth and then comes back is younger than the twin that stayed on the Earth, we realize that our ruler that we have been measuring with will always show the difference in distance in the direction of travel as the same as when we first set the experiment up. We also know that our ruler will also change length based on how we orient it. So, measuring the top distance between the beam splitter and the mirror in line with the blue colored line, our ruler will show 1 unit just as it did when we first set it up, because it is compressed to 1/2 its original length. When we measure from the beam splitter to the bottom of the mirror center, we will also get a measurement of 1 unit. And this is because when we rotate our ruler, it is no longer compressed along its length, but rather across its width, and its length would be the uncompressed 1 unit length. This is what we would expect because our clock is slow, and therefore we know that we are compressed in the direction we are traveling, because we are now at 0.866 the speed of light, and the compression is 1/2. Now the reasons the angles have changed is because the mirrors were at an angle, and when you compress a triangle along either the horizontal or vertical or both axes, it changes the values of the sine, cosine, and tangent, since one, or at least one of the coordinate distances, will be different, and in this case, one leg along the direction of travel will be one half of what it was initially, and thus the sine, cosine, and tangent would be different, and thus the angles have all changed. And since we know that according to the laws of physics, the angle of incidence on a mirror must equal the reflected angle, and those angles also all change. And since those angles have all changed, the beams are not going to the detector anymore. But then this is not actually an inertial reference frame because the rotating equipment is under centripetal forces and the linear acceleration experiment is under linear acceleration forces. So, in order to be a true test, we have to get to an inertial reference frame. That can easily be accomplished simply by slowing down the rotating equipment until it no longer has any angular motion. And that is what the rotating experiment team does. They bring their rotation to a stop and everything goes weightless. At the same time, we shut off our accelerator and go weightless. Both systems are now in an inertial reference frame within the accuracy of anything we can measure. At the rotating experiment, they observe, which is the same setup as they had when rotating when they started this experiment. On the other hand, what we see is, and we can verify by this that our 1g of force was an acceleration. The reason the reflected beams do not change when you eliminate your acceleration is because it is not acceleration that changes the angles on the mirror due to compression. What causes the compression is the actual speed you are at and the speed you maintain. Whatever speed you have when you quit accelerating determines what the amount of compression is. In the case of the spinning experiment, our beams changed position in proportion to our rotational speed in meters per second at 1g of acceleration. And even though the changes made are extremely small, if not so small they are undetectable by our sensors, they are still there. In the case of a rotating experiment, the speed will induce some distortion in the mirror's angles, which will stay at the value it was at when you stop changing the rate of angular motion. And therefore, if you have a method to measure the position of the beam at the detector, and that measurement changes as you go from weightless to 1g, and then stops changing, then you know you are in a circular motion. And that's of course assuming your rotational axis is in line with the blue line and you are moving towards the red line. In the case of the linear acceleration motion producing 1g of acceleration, the beam keeps changing with time even though you are still under 1g of acceleration. In the case of a uniform gravitational field, the beam path does not change if we remove the uniform gravitational field because the compression when your experimental setup is with the gravitational field vector coming in the top and out the bottom of the mirrors. Any distortion is in the vertical frame of reference rather than in the horizontal frame of reference, and thus no angles change, so the beams stay in the position they were at the start, regardless of what you do with the gravitational body that was pulling you down. The most you can say is that all three methods acting against any entity can produce at least the same amount of reaction by the entity being affected. You cannot say that all three entities produce the same result when they are removed, and thus they are not equivalent in their action. There are several other experiments you can do to show that equivalence is not a valid physical characteristic, and I will go over some of them later in other videos. Hey, would you happen to know where they keep the treats around here?